So today we're going to be going over simulating circuits with diodes in them in LTSpice, and we'll just do a basic voltage source with a resistor connected to a diode. And specifically, we'll simulate a constant voltage drop model, and then we'll look at how we can simulate other exponential and more accurate models than the constant voltage drop model. All right, so let's start out by putting in our components. So we need a voltage source. Oops. And we're going to need a resistor. And then also a diode. Okay, and then let's place the ground as well. Okay, and now let's wire everything up together. Oops. Okay, so we'll connect our voltage source to one end of our resistor. Other end of the resistor goes out to our diode, and we'll leave an outlet here to do our measurement on. And then we'll connect the other end of the diode to ground, and that will also be connected to the negative side of our voltage source. All right, so let's pick values for the resistor. Let's say we were going to do 1K. For the voltage source, let's go with 5 volts. All right, and now for our diode, what we're going to do here is create a model. So we're going to give this a name. We'll call it D_ideal. So now what we need to do is put in a model that corresponds to this ideal diode that we want. So the SPICE directive for that is .model, and then you give your model name, which in this case is ideal, D_ideal, and then we have D, and then we give it the parameters that we want to set. So there's a whole bunch of parameters, but since we're just doing the constant voltage drop, all we need is V forward, and let's set that to somewhere around 0.7, close to what a silicon-based diode would be. Okay, so that'll be the model used when we're running our simulations. We need one more thing on our circuit. Let's put down a net name called VD, and we'll put that right above our voltage, or our diode. So VD is the voltage drop across our diode. Okay, so that has everything set up. So if we wanted to do just a simple calculation with this setup, we could do, go to draft, SPICE directive, and then we would do .op. Okay, and then we can run it. Brings up that, and if we want to view all the outputs, we can go to view and then view your SPICE error log. Okay, and we can see our voltage drop across the diode is 0.7 volts with a little bit of a rounding error there, and that's what we would expect for a constant voltage drop model. The voltage drop should be equal to our forward voltage drop, which we set to 0.7. We can see the current running through the diode and the resistor is all the same. It's 0.0043 amps, or 4.3 milliamps, which is somewhere reasonable. Okay, and that's it. So that's for the basic simulation. If you just want to get the operating parameters for your diode operating at some voltage. So another thing we could do real quick, okay, what if we don't have enough voltage to turn it on. So let's say we drop this down to 1 volt. Then let's run it again. Okay, so now let's look at our error log, our output. Okay, so we can see that at 1 volt we still turn on, the voltage drop is about 0.7, and our current now is much lower though. We're at 0.3 milliamps, so if we take it, let's see, take it down to, let's say, 0.5 volts. Okay, run again, let's view our log again. Okay, so here we see finally that we're at our basically zero current, so our diode is basically off because our voltage drop isn't enough to get it to go through, isn't enough to turn on the diode. So we could walk through like that to see when it eventually turns on or off, but another way is to use a sweep parameter, spice directive. So to do that, we could go .dc. Then you give it the name of the variable that you want to sweep. So in this case, we want to sweep our voltage source. So we'll say V1. Let's start at 0. Start at 0. Almost 0 volts. Let's go up to 10 volts and let's step by 0.01 volts. So this tells you you're doing a DC sweep on our voltage source V1, starting at 0.01 volts, going up to 10 volts, and going by increments of 0.01 volts. All right, so we'll do that. We'll do our run, and this time we're going to want to plot. So let's plot an IV curve. So we need to add a trace, and we want to add our current going through diode 1, so it's ID1. And then let's, on the bottom here, plot the voltage from our diode, across our diode, VD. Okay. So let's change the scales here a little bit. Let's go out to 1 volt. Let's change the scale here. Let's go up to 1 milliamp. Okay, so not the prettiest graph. You can go in and fix that a little bit more, but you can see sweeping across that our diode basically doesn't turn on until we hit 0.7 volts. Once we have that voltage drop of 0.7 volts across that, it allows current to flow through, which is consistent with our constant voltage drop model. Okay, so the other thing we can do is to, instead of using an ideal diode model, we can switch out and use an actual real model. So LTSpice has some baked in. So if you left click on the diode, it'll bring up this menu. So we can go in and pick a new diode. Let's just pick the 1N914. Okay, now let's rerun our simulation with that. And now you can see instead of our constant voltage drop model, we have the exponential model that you would expect. So it's a little bit more accurate. And you could solve this by hand, but again, LTSpice can do this all for you and it has built-in models. So this is one of the more accurate ways if you're looking for the exact values that you're going to get. And also you can just do an op simulation. So again, this was a sweep, but we can switch back just to an operating point. So go back to .op. Let's run again. And let's look at our logs. So there we go. Vn is 0.5. We basically have no current flowing through at this point. So let's modify that. Let's change this to back to 5 volts. Okay, and then rerun. And here we go. If we look at our log again, so now we see we have a voltage drop of about 0.65 volts across our silicon diode, and there's a current flowing of about 4.3 milliamps again. So this is actually pretty close to the result that we got with our constant voltage drop model, but again, it'll be more accurate at lower voltages and higher voltages than the constant voltage drop model will be. Okay, so that ends the simulation steps.